Hi guys, so in this lecture video, I'll be teaching you guys about stoichiometry. Now stoichiometry is basically a types of chemical calculations that involve the use of relationships among the ingredients. So a chemical equation, it basically, we can think of it as a recipe, right? A cooking recipe. For an example, here in making of this pancake right here, we would need to add flour, and we need to have to use eggs and baking powder, and from there we can make this pancake right here. So this is a cooking recipe, and here in this case right here we can see that the three ingredients that we need to use, right? So the flour, and we can think of this as the reactant 1, and the eggs would then be the reactant 2, and the baking powder would then be the reactant 3. And using these three reactants, we will be able to make the pancake. And the pancake here in this case right here would then be the products. So if you have made pancake before already, then perhaps you need to follow a recipe, right? And do some sort of calculation in order to make the amount of pancake that you want. And in fact, if you don't follow the recipe, you will not be able to make your pancake. For an example, follow this recipe right here. If you were to use 1 cup of flour, you will need to use 2 eggs and add in 1/2 teaspoon of baking powder, and with that you'll be able to make 5 pancakes. Okay, so that's the basic recipe right there. And now let's say you have 5 cup of flour, then how many eggs do you need to use then? So you can see you have to do some calculation, right? And right now you can basically figure this out pretty easily. If you were to have 5 cups of flour, you will need to use 10 eggs. Isn't that right? And if you were to have 5 cups of flour, you will be able to make 25 pancakes, right? So these are some of the very basic calculation that we can all see easily, right? And anytime that we have to calculate the amount of one reactant, for example, the eggs, starting from the certain amount of the flour that we start out, then this kind of calculation right here are then collectively referred to as stoichiometry. Okay? And let's say that you want to make certain amount of products, let's say 50 pancake. How much of flour, eggs, and baking powder would you need? So again, if you are doing those kind of calculation, then you are doing stoichiometry. Okay? So don't let this name scare you. If you have followed a recipe to make something before already, then you can do this. You can do stoichiometry. And now, let's now put this into the chemistry perspective. So in chemistry, we have the chemical equation. And a chemical equation is very much similar to a cooking recipe. In the chemical equation, we have the different reactants that are involved, right? And making different products as well. So what kind of relationships between those reactant to products? For example, if I were to have certain amount of one reactant, how much of the other reactant would I need? And how much product can I make from there? So that's the kind of calculation that we are doing here in chemistry. And these are chemical calculation, or also known as stoichiometry. So everything go back to the chemical equation. The chemical equation, just like cooking recipe, it gives us a lot of qualitative and quantitative information. Now, qualitatively speaking, it tells us what kind of substances are being involved. Just like this cooking recipe right here tells us that we need to have flour, eggs, and baking powder, right? And now, quantitatively, it shows us how much of the amount of certain substances they involve in the chemical calculation. And it mainly uses something that we call the numerical ratio, such as the stoichiometric coefficient or the factor. Now, so it shows us those qualitative information right here because the substances and the product in the chemical equation are related by those stoichiometric coefficient or factors. For an example, if this cooking recipe right here, if this pancake recipe right here is a chemical equation, then the value 1 here, 2 here, 1/2 here, and 5 here, this will be the value that you will be adding in to make sure you have a balanced recipe, right? Or a balanced chemical equation. So this is what this coefficient would be. These are the quantitative information that we would obtain from the chemical equation. Okay. And so in a chemical equation, there are many relationships between the reactant to reactant and product to product and reactant product that we can derive by using the stoichiometric coefficients. And all of these relationships right here are useful. And in fact, we need to be able to identify all of this relationship because we can use this relationship right here as conversion factor that will then allow us to do all of this calculation right here. For an example, let's say here, this pancake experiment or recipe is a chemical equation. What kind of relationship can we get from this pancake recipe right here? So first, here are a few types of relationship that we can get. And this can be broken down into 3 types of relationship. First would then be a reactant to product relationship, in which we can pick up any of the reactant and draw relationship to the product. So for an example, we can draw relationship between the flour to the pancake, in which 5 pancakes are produced for every 1 cup of flour, right? So that, because the flour is a reactant and the pancake is a product. So this would be an example of a reactant to product relationship. Now another example would be 2 eggs would produce 5 pancakes. So again, we can pick up any of the reactant and then draw its relationship to any of the products. And so let's say here, let's go back to the relationship between the pancake and the flour. Then we can see 5 pancakes are produced for every 1 cup of flour. So this is a relationship. And from this relationship right here, we should be able to write the conversion factors. And in fact, it is very, very important that we know how to come up with the conversion factor for every one of this relationship. So here in this case, we can rewrite this as follows. 1 cup of flour equal to 5 pancakes. So they equal to each other. And from there, we can write a set of 2 fractions that are reciprocal, that are essentially the same thing. We can write 1 cup of flour over 5 pancakes, or the reciprocal 5 pancakes over 1 cup of flour. So this relationship right here is useful anytime we need to do some calculation between the flour to the pancake. For an example, if you were to have 5 cups of flour, how many pancakes would you be able to make? In order to do that calculation, you will need to use the relationship between the flour to the pancake. And here in this case, we can see easily that you would be able to produce 25 pancakes from 5 cups of flour. Okay. And so another types of relationship that we can also get from the chemical equation would then be the reactant to reactant relationship. So we can pick out any of the 2 reactants and draw relationship among them. But it's really important that we use this coefficient right here as we draw the relationship. And for an example, the relationship between the flour to the eggs is as follows. 1 cup of flour would require 2 eggs. Right? So here in this case right here, we will then see that 1 cup of flour equal to 2 eggs. That's the relationship. And again, from here, we can write a set of 2 conversion factor as well, or 2 fraction, in which we have 1 cup of flour on top and 2 eggs on the denominator, or the reciprocal 2 eggs on the numerator, and then 1 cup of flour on the denominator. Now this conversion factor right here and this relationship will be useful anytime that you have certain amount of eggs and now you need to calculate how much flour that you would have to add and so on. But it will allow you to calculate the amount between the flour, the cup of flour, and the eggs. Good. And the third type of relationship would then be the product to product relationship. And here in this case right here, the example of the pancake is not relevant because we have only one single product. But in most chemical reactions, there'll be multiple products. And now we can also draw product to product relationship as well. But now let's go back to the main thing. So it's really important that we have a chemical equation that is correctly balanced. And the ratio or the coefficient that we use to balance the chemical equation then tell us the relationships among the different reactants and product in that balanced chemical equation right there. Okay, and again, we should be able to recognize the three types of relationship: reactant to product relationship, reactant to reactant relationship, and product to product relationship. And more importantly, know how to derive the conversion factor from this relationship, because this is very important to be able to do chemical calculation. Okay, and now let's switch gear a little bit, and now let's apply this to chemistry. So in chemistry, very important, for any chemical equation that is correctly balanced, we can draw the mole to mole relationship among the different reactants to reactant, product to product, or reactant to product by using those coefficients right there. Good. So again, every quantity or every reactant and the product in a chemical equation that is correctly balanced are now related to each other in a mole to mole basis. Very important. Now the reactant and the product are not related in mass to mass, but now mole to mole. So this is why knowing how to use the mole and calculating the mole is really important here in chemistry. For an example, let's say if we were to consider a combustion reaction of octane and write in the balanced chemical equation for this. So the balanced chemical equation for the combustion of octane is as follows. And here, in order to make sure this is balanced, we need to put 2 right here, 25 right here, 16 and 18 here. So these are the coefficients that we need to put in to balance this equation. And now let's come up with the reactant to reactant relationships from this balanced chemical equation right here. So why do we need to be able to identify the reactant to reactant relationship? The reason why that is important is as follows. So if we were to have certain amount of one reactant that we use in a chemical reaction, how much of the other reactant would be needed? And you can see that this is a very basic types of calculation that we would need to perform here in chemistry. Given the amount of one reactant, how much other reactant would be needed? In order for us to solve that kind of problem, we need to be able to identify the reactant to reactant relationship. And here in this case right here, this would be the reactant to reactant relationship. 2 mole of octane require 25 mole of oxygen, right? Because the coefficient 2 and the coefficient 25 are needed to make sure this chemical equation is balanced. So from this chemical balance right here, we'll be able to say that for every 2 mole of octane that being used, we will need 25 mole of oxygen. So that's how this coefficient come in. They become the mole to mole relationship among these 2 ingredients. And from this relationship right here, we can write this following conversion factor. 2 moles of octane over 25 mole of O2. Or the reciprocal, where we will put 25 mole of O2 on top, and now 2 mole of octane on the denominator. Okay, so these 2 fraction right here are used for different purposes. This first conversion factor right here is used to convert the mole of oxygen into the mole of octane, versus the other fraction over here is used to convert the mole of octane into the mole of oxygen. So if we were to have certain mole amount of octane, how much oxygen that you would need, then we'll be using this fraction right here, versus this other fraction here is used for the other conversion. Okay, so we always end up with a fraction on top. Okay, so and now let's now go over an example of a reactant to product relationship. When do we need to use this reactant to product relationship? So here's when. So if we know certain amount of one reactant being used, how much product it produce then? Okay, so if this much reactant is used, how much product would be produced? And so here in this case, right here, we can see that 2 mole of octane will produce 16 mole of CO2. So if we were to go to this equation right here and draw the relationship between this reactant to this product right here, then 2 mole of octane will produce 16 mole of CO2. So that would be one of the types of calculation that relationship that we can derive from this chemical equation. So here in this case right here, we can write this following conversion factor. 2 moles of octane over 16 mole of CO2, or the reciprocal of it, where mole of CO2 is on top and mole of octane is on the bottom. So that will be the first time, or one of the examples of when we need to use this reactant to product relationship. That if we were to use certain amount of reactant, how much product is being produced. And now here is the other way right here. We can also go the other way around. If we need to produce certain product, how much reactant do we need to have, or how much reactant would be consumed to produce certain amount of product? That is another types of relationship that we can also get from the reactant to product relationship. Okay, so here in this case right here, we can also do the following. An example: 18 mole of water require 2 mole of octane. And from there, we can write this relationship: 18 mole of water over 2 mole of octane. Okay. And the third types of conversion factor or relationship, product to product relationship. And the usefulness of these types, or to be able to identify this type of relationship, is whenever we have certain amount of one product is being produced, how much of the other product would also be formed as well. Let's say if we were to have a chemical equation where there are different multiple products being produced. So here in this case right here, we will then see for this reaction, there are 2 products, CO2 and water. And based on the coefficient that we see right here, for every 16 mole of CO2 that are being produced, 18 mole of water are being produced as well. Okay, so therefore that becomes the conversion factor that we would use to figure out the amount of one product that will be produced when certain amount of other product are known to produce already. So here in this case, we will be able to write 18 mole of water over 16 mole of CO2, or the other reciprocal of this conversion factor right here. Okay, so knowing how to identify this relationship right here and know how to write the conversion factor are really important. And so the chemical equation offers us with so many relationships that, and so we have to ask ourselves this question: what relationship will be relevant for me to come up with, right? So that depends on what is being asked in the problem. That's how you, based on the question being asked, you now can identify what types of relationship that you would need to use in order to solve that problem. Okay, and let's now try an example right here. Let's say here is a problem. How many mole of CO2 are produced from the combustion of 22 mole of octane? So if I were to burn 22 mole of octane, how many mole of CO2 would be produced? So let's solve this problem right here by using dimensional analysis. So here in this case right here, I'll start in unit. The starting unit would be 22.0 mole of octane, CaH18. And the wanted unit will be the mole of CO2. It's important that we identify the starting unit and the wanted unit. So that way we know what kind of relationship that we need to use. So here in this case right here, we are starting from mole of octane. This is a reactant right here, right? And mole of CO2, and this is a product. So this problem right here involves the use of a reactant to product relationship in order to solve it. So therefore, the conversion factor between this reactant octane to this product CO2 will be as follows. Based on the chemical equation we have seen already, between octane and CO2, it'd be 2 mole of octane will produce 16 mole of CO2. So that's the relationship or the conversion factor that we need to solve this problem. 16 mole of CO2 over 2 mole of octane. Okay, and now let's solve this problem right here by set up the dimensional the analysis and the conversion pathway. So we will be starting with 22.0 mole of octane, and we want to convert this into mole of oxygen, and this is the conversion factor right here. So we want to get to mole of CO2, so we're going to put that in on top, right? And we want a mole of octane to be cancelled out. So we put in 2 mole of octane on the denominator. And now 16 mole of CO2 on top. And when we do this calculation, the mole of octane will be cancelled out and we'll end up with mole of CO2. And when we take 22.0 multiplied by 16 divided by 2, we'll be getting 176 mole of CO2 that would be produced. Good. And here in this case right here, we will be rounding our answer to 3 sigfig. And the reason why is as follows. The mole to mole relationship or the mole to mole ratio from the balanced chemical equation, these are exact value right here. Okay, so we do not, they are counted as having infinite sigfigs, or we do not count them in determinate amount of sigfig. So here in this case, this value right here have 3 sigfig, and that's why we rounded the answer to 3 significant figures. And now let's go over how do we do stoichiometry problems for a real chemical equation. Okay, so first, please remember that in a chemical equation, the reactant and the product are related in a mole-to-mole basis. Once we have the chemical equation correctly balanced already, the coefficients that we put to balance the chemical equation become the mole-to-mole relationship among all of the reactants and the products in that chemical equation. And whenever we solve stoichiometry problem, then we need to convert the amount of the starting unit, whatever that you starting out with. You have to convert that amount into mole first by using its molar mass. Because we have to convert the amount of the first reactant into mole. So that way we can use that mole-to-mole relationship to relate that to the product or to the other reactant that we need to. And we can also do a molecule-to-molecule conversion as well by using the Avogadro constant as the conversion factor. And so let me explain this more clearly by using this diagram right here. These are basically the types of problems that students will be asked in general chemistry classes. So let's say that we were to start with the certain gram of a reactant A. And now we can be asking students the following. How many grams of the product would then be being produced? If we have certain mass of reactant of one reactant, how much product would be produced? To be able to solve that kind of problem right here, here would be the solution map. Starting from the mass of the reactant A, we want to use the molar mass of the reactant A to convert this into mole of the reactant A. And once we have the reactant A in mole already, we can use the coefficient from the chemical equation to now convert that into mole of the products. And if we are now asked for the gram of the product, you will then use the molar mass of the product to then get to the gram of the product. So this would be the solution map, how we would go from mass of the reactant into mass of the product. If instead of asking for mass of the product, that we now want to ask for how many molecules of the product would then be produced, then the solution map would then be as follows. Instead of using the molar mass above here to get to gram, you'll be using the Avogadro constant to now get to the molecule down here. Okay. And similarly, if we were to now start out on the reactant into the molecule, let's say have certain molecule of reactant A, how many molecule of the product would be produced? Then again, starting with molecule of reactant A, we have to convert that into mole. Okay, to convert mole from molecule into mole, you have to use the Avogadro constant at the conversion factor, and that will then get us into mole. And then we would then use the coefficient again from the balance equation to get to more of the products, and we would then use another Avogadro constant to now get to more of the products. Okay, and similarly, if we were to be asking, let's say that if we were to be asked, let's say we have certain mass of reactant A, how much mass of the reactant B would then be required? Then the process would then be the same. Starting from the mass of reactant A, we would then need to use the molar mass of reactant A to get into more of reactant A. And again, use the coefficient from the balance equation to now convert that into the reactant B, to the mole of reactant B, and then to the gram of the reactant B. Okay, so this would be, this table right here basically outline the solution map, how we'll be able to do all of the conversions that you would need to perform in chemical stoichiometry. And down below are the more guided, the step-by-step method how to solve all of the stoichiometry problems. So here are the steps right here. First, start by writing the balanced conventional chemical equation first, and make sure your chemical equation is correctly balanced. And next, find the starting unit and the wanted unit. It is then the starting unit and the wanted unit that then allow us to figure out what relationship or conversion factor that we would need to solve the problem. And after we have done the step 3 already, the next step would then to formulate a solution map, how to solve the problem first. So what are the steps that we need to take? And the steps that we need to take are then basically outlined in here. So these are the steps right here. Okay, for example, if we need to convert from the gram of reactant A into the product B, into the product, then the solution map will be going from gram of the reactant A into mole of reactant A, and then mole of reactant A into mole of the product, and from mole of the product into gram of the product. So that would be the solution map as outlined by this diagram. So make sure we formulate that solution map first before you put anything down to solve the problem. And finally, use dimensional analysis to solve the problem. Do not use algebra, okay? But dimensional analysis is really the easiest way how to solve this kind of problem. And now let's try a few of the practice problem right here. So here's the problem. How many grams of oxygen would be required to burn 24 grams of octane? Okay, so anytime that you have been asked, for example, how much of one reactant do we need to use to react with certain amount of the other reactant? So based on the context of this problem right here, this is stoichiometry, because that's what the question asks is. How many grams of oxygen is required to burn this much gram of octane? So we know that we are dealing with a stoichiometry problem. So therefore, make sure we follow the step. And again, the first step is to write the balance equation. And the balance equation for this reaction, as we have worked out previously already, is as follows. 2 mole of octane combined with 25 mole of oxygen. And that will then produce 16 mole of CO2 and 18 mole of water. So that is the balance equation right there. Okay, so that's the first step. If we don't have that, then make sure you work that on that first. And now the step 2, identify the starting unit and the wanted unit. based on this problem right here, what are the starting and the wanted unit? So here in this case, we're starting with 24 gram of octane. So 24.0 gram of octane. And the wanted unit, how many gram of oxygen, right? So question mark gram of oxygen. That would then be the wanted unit. Now, once we have identified the starting unit and the wanted unit already, we can see that we need to convert between the gram of octane into gram of oxygen, right? And octane is a reactant. And oxygen is also another reactant as well. So here in this case right here, the relationship that we need to use is basically a reactant to reactant relationship. And now this reactant to reactant relationship based on the balance equation is 2 mole of octane to 25 mole of oxygen. So the needed conversion factor in this case right here would then be 25 mole of O2 over 2 mole of octane, or the reciprocal of this fraction. And now let's now formulate the solution map. So the solution map is as follows. We starting from the mass of octane. And now we need to convert this amount into mole first. So we need to convert this into mole of octane by using the molar mass of octane. And once we have mole of octane already, we can use the coefficient or this conversion factor right here, or this relationship, to now convert this into mole of oxygen. And once we have mole of oxygen already, we can use the molar mass of oxygen as the conversion factor to now get to gram of oxygen. And this would then allow us to get to the wanted unit, starting from the gram of octane. And now let's set everything up by using dimensional analysis. So we're starting with 24.0 gram of octane. And now we need to convert convert gram of octane into mole of octane. So we would need to have the molar mass of octane. And the molar mass of octane is 115.23 gram of octane. And we need to put this on the denominator so the unit gram can get cancelled out. And on top, we have 1 mole of octane. And now we can see gram of octane will cancel with gram of octane. So there we are now at this step right here. So the next step is for us to convert mole of octane into mole of O2. And again, this is the relationship. So we will be putting here on, we will be putting mole of octane on the denominator. In this case, 2 mole of octane. And on top, we have 25 mole of O2. And now the mole of octane will be cancelled out. And the next step would now be converting mole of oxygen into gram of oxygen by using the molar mass of oxygen. And now we will put it on the denominator, 1 mole of oxygen. And on top, we have 32.00 gram of oxygen. And there we go. Now mole of oxygen will be cancelled out. And we will end up with gram of oxygen, which is the unit that we need to be solving for. So now we need to plug all of this into the calculator. And the answer would then be 83.3 gram of oxygen. And we need to round this answer right here to 3 significant figures. And the reason why is as follows. So this first value right here have 3 significant figures. And the molar mass here would then have 5 significant figures. Now please remember this. All of this mole-to-mole relationship right here are exact value. And they are then said to have infinite amount of sig fig to it. And here this molar mass right here have 4 significant figures. So therefore we need to round our answer to 3 significant figures. That's the quantity with the least amount of sig fig on it. Okay. And now let's try another problem right here. So why don't you take a minute to work on the example 2 and 3 before we go over the answer together. Okay. And I'm going to assume you have done this already. And so I'm going to go over the answer with you guys together. And here on this, I'm going to show you guys, so again, a faster way how to solve this problem, how to solve stoichiometry problem. Okay, so these are the 5 steps. And we're not skipping any of this step. Okay, so please remember that there is no skipping of any of this step at all. There's a faster way how to set it up, but we still have to be able to do all of this step right here. And by skipping step, that's how we get ourselves in trouble. Okay. Now, so we don't want to be writing out the work for all of this step. That's how we can speed this up. But again, we have to do all of this step 1 to 5 right here. So here in this case right here, we have a balanced equation already. And this question is as follows. How many grams of CO2 would be produced by burning 66 grams of octane? Okay, so we know the CO2 is a product, right? And we know octane is a reactant. So in this case right here, we now have a balanced equation. So the next step is for us to identify the starting and the wanted unit. And this is a very neat way of listing the starting and the wanted unit. So our starting unit here is 66 grams of octane. You will then go to the balanced equation, and right below octane, you will then put in 66.0 grams of it. So this means that we have 66.0 grams of octane, the starting unit. And now the question asks how many grams of CO2. So you be going to CO2 and put a question mark and gram right next or under CO2. So this tells us that this is the wanted unit right here. So this is a very neat way of listing the starting and the wanted unit. Okay, by putting the information below the substances on this balanced chemical equation. So here in this case right here, once we put this information down, we know that octane is a reactant and CO2 is a product. So we need to have a reactant to product relationship in order to solve this problem. And the conversion factor regarding this reactant to this product right here will be 2 mole of octane producing 16 mole of CO2. So keep that in mind. That's the relationship that you would need to use. Okay. And now let's go over the solution map. We're starting from gram of octane. So what we have to do first is convert this into mole. So basically from gram of octane. The solution map is something that is worth writing out. Okay. Into mole of octane. And once we have mole of octane already, we can now convert this into mole of CO2. And for mole of CO2, we can now convert this into gram of CO2. So that would be the solution map. And now let's set this up and solve this by using dimensional analysis. Starting with 66.0 gram of octane. We need to first convert this into mole of octane by using the molar mass of octane. And the molar mass of octane is again 115.23 gram of octane. And we're going to put this unit on the denominator so it can get cancelled out. And on top will be 1 mole of octane. And now we can see for every 2 mole of octane that we are using, it'll be producing 16 mole of CO2. So therefore, I'll be putting 2 mole of octane on the denominator. Producing 16 mole of CO2. We'll be putting that on top. And now we need to convert mole of CO2 into gram of CO2. For every 1 mole of CO2. And again, this will be put on the denominator. And on top, it will be 32.00 gram of, that the molar mass of CO2 is actually 44.0 gram of CO2. And there we go. Now, to double check the work, we want to make sure that all of the units that we don't want should get cancelled out, right? So mole of CO2 cancel with mole of CO2, moles of octane cancel with mole of octane, gram of octane cancel with gram of octane. And here in this case, we'll end up with gram of CO2, which is what we're supposed to be solving for. And here in this case, we'll then equal to 202 gram of CO2, rounding to 3 significant figure. Okay. And now let's go over number 3 together. So if 202 grams of CO2 is being produced, how many mole of water would also be produced then? Because in this equation right here, we can see that CO2 and water are the two products, right? So here in this case right here, in order to solve this problem, we need to use a product-to-product relationship. Good. So here in this case, we have our balance equation already. And now the starting unit here in this case right here would then be 202 grams of CO2. And now the wanted unit asks for mole of water. Please note mole of water, not gram of water. So we asking for the amount of water. And here in this case, mole of water. So that's what we have right here. So we starting from gram of CO2 and we want to convert this into mole of water. And so the solution map would then be as follows. Starting from gram of CO2, we need to convert this into mole of CO2. And now for every 16 mole of CO2, it would be producing 18 mole of water. And that would then be the solution map. And now let's set this up using dimensional analysis. Starting from 202 grams of CO2. And now we need to use the molar mass of CO2 to get this into mole of CO2. And the molar mass of CO2 is 44.0 grams of CO2 equal to 1 mole of CO2. And for every 16 mole of CO2, and we're putting this on the denominator, so that way mole of CO2 can get cancelled out. And on top, 18 mole of water. And there we go. So mole of CO2 cancel with mole of CO2, gram of CO2 also get cancelled out as well. And we will end up with mole of water. And here in this case, we're equal to 5.16 mole of water. And we'll be rounding this answer right here to 3 significant figure. Okay, this value right here have 3 significant figure. This have 3 significant figure. And this ratio right here, mole to mole ratio, have infinite amount of significant. So therefore, the value, the quantity with the least amount of significant is 3. And that's why we're rounding this to 3 significant figures.